Hello and welcome to Chapter 20, which we're going to use to talk about the design and analysis of experiments and observational studies. Previously in Stat 1, you've talked about survey analytics and how to discuss and analyze those, but so far you haven't really done anything with experiments or observational studies. So that's what we're going to be focused on today. So this chapter is actually sort of the spiritual successor to Chapter 14, which was the chi-squared, because in that we really saw a comparison across many different proportions across many groups. And in here, we're going to look at comparing means across several groups. Now, we've done two. That was our test of two means and two proportions. When this is really the first time we're going to be able to do many means across many different groups for experiments. Okay, so the first type of thing we're going to be looking at is what's called an observational study, or well, just observational experiments. So what's different about an observation is, well, it's like observing something. You don't interact with it at all or adjust it in any way, shape, or form. So lots of companies collect data this way. If you've ever had a frequent buyer card, or if you're like a member of Target's Red Card group, or basically any type of incentivization with coupons where they track your spending and offer you points or something like that in exchange for information, you've actually been participating in an observational study where they follow your buying habits to see what they can do to incentivize more buying for you. So there's really two big types of observational studies. Studies can be retrospective, where they look at historical data and try to use that to decide what the trends are for their company. Or we can look at what's called a prospective, which is when they seek to identify in advance what's going to be happening. So prospectives are usually longer or longitudinal in their nature. Will start and go on for several years. This is also more typically seen in medical testing, as well as some of the other things we're going to see today as well. So the example I gave here was following a sample of smokers and runners to see whether or not one group or the other had a higher occurrence of emphysema. So prospectives usually go over many years, just so you're aware. Okay. Next, let's talk about an experiment. So an experiment has to be manipulated somehow. So you're, of course, picturing the mad scientist tapping his fingers together and going, "Wah ha ha," but really, yes, you are going to be manipulating your data in some way, shape, or form. So the idea is that you want to assign your groups different options that will, see if those options create better results than others. So when we look at the options that you would assign, those are called factors. And then the different values you can have in those factors are called levels. And when you combine the different levels from all the factors that you have, those are called treatments. So we'll have what are called treatment groups at the end that describe all the different factors and all the different levels that are present in our experiment. And these can get quite complicated very quickly. So the two key features that you can use to distinguish these from each other is that, well, an experimenter actively and deliberately assigns and manipulates factors according to different subjects and places them in their treatment, and an experiment must assign subjects to those treatments at random. So observational, usually there's no random assignment, and the individuals assign themselves, so there's no randomization that occurs in observation. The other thing to keep in mind is often when it comes to certain experiments, you can't unassign people to things sorry, what am I trying to say here? Yes, you can't change treatments is the other thing to keep in mind. They stay within the treatment group through the entire thing. Sorry, I was going to say unassign it a group. No, yeah, you get the idea. Okay. So here's an example for you. A soft drink company wants to compare the formulas they have for their cola product, and it's treated with its cola with different types of sweeteners, either sugar, corn syrup, or artificial sweetener, and all the ingredients amounts were about the same, and then they have 10 taste testers rate the colas on a scale from 1 to 10, and then the colas were presented to each tester in a random order. The reason you do a random order is because more often than not, people will rate things better at the beginning of a study than they will at the end, so randomization will allow you to prevent that sort of bias being present there. What we want to do here is identify the experimental units, the treatments, then the response for the random assignment here. So the experimental units here were the colas, so that's what we were trying to discover. The treatments that we were assigning them were the different sweeteners to those colas, and then the response was their taste rating that we would get. So the random assignment is the random order that the taste testers were presented the sodas. So this is a comparative experiment that has a completely random design. All right, so let's talk about the 4 principles of experimental design. The first thing is a control. We control variation by comparing and testing groups against a group that's not really given a treatment, and that group is called your control group. Controlling usually tries to temper out any access source of variation. Human beings are very unique by nature, and because of that, there are lots of other things that can seem like they're causing differences in your values. So you want to allow for that variation to be present. Not every experiment will have a control, particularly in medical testing where they are dealing with a deadly disease. They can't assign you no treatment or put you into a control group like that. So the problem is you could willfully kill someone, so they usually are comparing 2 different treatments instead of assigning one group treatment and one group no treatment. That would be bad. All right. I mentioned this already. We call this group the control group, and they sort of give you your baseline measure for whether or not you have a difference here, or if that difference was just random chance and not really a difference at all. So there you go. All right, the next thing is we want to include randomization. Randomization is the best way to spread out any sources of variation or error across the entire group and across all treatments. The other thing that's good about randomization is it prevents any bias you might have towards certain individuals that are present in your data. Like if you have one experimental unit that you think is more likely to produce good results, this will prevent that from happening as far as the experimenter goes in comparison to the subjects. So just, keep that in mind. And the other thing is randomization, as we know, always guarantees that we'll have a more representative sample than if we had assigned it ourselves. All right. The next thing we want to have is replication. Now, not all studies are easily replicable, but if you have a good study or good experiment, then it will be replicable. So the idea is that if somebody can repeat the experiment and see the same results, you have done a good job. And this is really the hard and fast judgment of whether or not you have got a good and true result. And what we want to be sure we're careful about with this is that you have when you replicate, you try to keep the same number of combinations as in the same treatments. You don't change your treatment method midstream. And that's what we call a balanced experiment, because everything is receiving the same amounts. The second type of replication is to repeat the experiment entirely. Frequently when it comes to scientific data or repeating an experiment, what you'll do is you'll have a different experiment repeat the same thing that you have done to see if they produce the same results as you. This level of replication is to guarantee that you have good results. So this is also done in computer science as a fun fact. When people have a code and they want to see if it produces good results, they'll have someone else go repeat their actions using a different computer to see if they produce the same results. And this is very frequently done in statistics in particular, especially when it comes to a new calculational type or new type of testing. All right. Whew. Number 4. Hey, good times. So the last thing we're going to talk about is what's called blocking. This is how you want to group your subjects in order to make sure that some factor in particular may or may not cause differences amongst your group. So the usual typical thing we're careful about with blocking is factors like gender or sex, ethnicity, marital status. Age is another big one. Oh, I didn't write that one in here. In particular, if you think that one of these could be an additional factor that could affect your experiment, you want to make sure that they're blocked apart from everyone else so that you're keeping track of those blocks and seeing whether or not they're having an effect on the experiment. So this is basically the exact same thing as the stratified sampling method, if you remember that from back in chapter 8 a long time ago. So the idea is that by blocking, we're going to make these groups more homogeneous. They're more similar, and that way we can discern whether or not that block factor is actually a factor itself, or if it's just something that doesn't matter at all. So blocking isn't one of the ones that's required in order to have a good experiment, but if you suspect something like, oh, I think gender will have an effect on this, or I think age will have an effect on this, you prepare for it ahead of time to make sure that you get more homogeneous results and actual results rather than having the block affect what's going on. Alrighty. So when you're approaching your design, the one thing we want to do is something that's called a completely randomized design. These are the best types of experiments. They're also the simplest and the easiest to analyze out of all of them. So the biggest thing is that when it comes to assigning treatment, at least one subject is assigned at random, and therefore the design is completely random. So let me take you into what this looks like. So the idea is that we will randomly allocate individuals into different groups and then randomly assign those groups treatments. So as you start the design, you don't necessarily know which group is getting which treatment until you hit that second randomization. So random, random, and then you compare your results. So if you have one of those blocking factors that you're worried about, and these are not ones that you can actually assign to people, in case that was unclear, you can't assign someone a age, sex, or gender as much as you might want to. That's their choice. I don't think you really get to choose your age, although if you ask my mom, she's still 20. It's fun. So you want to separate your blocks first and then do your randomization. This is called a randomized block design. It does have a little bit of a difference from the completely randomized experiment, since you cannot control what that block factor is going to be doing. So just like before, I want to show you an image of what this looks like. So we're going to look at an example. So we're going to look at a marketer who wants to look at different spending groups and offer them different offers to see, hey, is the different offer type going to cause different spending behavior in these two groups? And clearly when he looks at the individuals in his spending groups, he can't really control whether or not they're a high spender or a low spender. That's definitely your block. And then the offer is the thing that you're controlling, so that is going to be a factor that you assign randomly. So here's how this process looks. So what you do is you block off, so you've got basically select enough customers to where you get equal groups, and that'll make sure that you have a balanced design. So you take an equal number of individuals from each group, the low spending and then the high spending group, and then you randomly assign them to different treatment groups. So group 1, group 2, group 3, and you do that to the high spenders as well. This is where the random assignment's coming in, so I'm about at the middle of this now. And then we randomly assign those groups to treatment. One group gets the control, and then the other two treatments are the offers we offer them. So maybe we gave them double miles on their credit card, or we gave them a free airline ticket, and so on and so forth. And then you compare your acquisition rates. So acquisition rates are all about spending, whether or not that increased their spending rates, to see if you can determine which offer is the best to make you get more business. So this is what that looks like. So basically, when it comes to blocking, you always take care of the block first, and then you randomly assign to create your groupings before you randomly assign your treatments. Alrighty. Occasionally, you'll have something more than just one treatment that you want to be dealing with, or more than one factor. When this is the case, you'll have what's called a factorial design. These get large very quickly, and if you're manipulating more than one factor at the same time, you might have them interacting with each other and causing a combined effect. If the experimenter does not contain both factors, you won't be able to notice this interaction that they're having. So you have to test for all of those. And as I said before, this gets a little bit more complicated, but at the same time, it's easier to see which combination has a better effect if you do all of them together. And you can also detect them individually with the type of test we're going to do. So not only will we be able to see if there's a single factor that's causing increases or decreases, but we'll also be able to see if there's certain combinations that are better than others. Alrighty. Another thing to keep in mind is that often experiments will have what we call blinding. This is where the person assigning the treatment doesn't know whether or not they're assigning a they don't know if they're assigning something that's good or something that's doing nothing. So usually with the control group, you're essentially doing nothing but making them feel like something is happening. And if the person who's assigning or delivering that treatment doesn't know if they're delivering something good or not, this is less likely to cause them influence and bias towards what could be happening. So the two examples of this are what are called a single blind. This is where one or both groups is blinded. One or the other is blinded, and the double blind is where both groups are blinded. So when you're thinking about single blind, think, oh, the person delivering treatment doesn't know what they're receiving, and neither does the individual. I just described double blind. And single blind is where the group who's receiving the treatment does not know what they are receiving. So it'd be like if you were receiving some drug and asking, are you experiencing more pain relief? The individual who's handing you the drug would know whether or not they're actually giving you a pain reliever, and you wouldn't know. That would be single blind. If you both didn't know, both the person giving it to you and you taking it, that would be a double blind. Let's look at another example of this. Oh, sorry. Examples in a minute. I turned the page. Usually when we are doing a blinding experiment, we have a fake treatment that's called the placebo. Placebos are important because often individuals will think they are feeling better when they receive a treatment, even if that treatment does nothing, just because they are getting something, you know. It's interesting. This is also called the placebo effect, where you'll start to feel better even though you're receiving nothing, just because you feel like some action has been taken. All right. So one of the problems with the placebo effect is it also can be misconstrued as something that's called a confounding variable and or a lurking variable. We talked about lurking variables back in chapter 8. There's something else besides your variables that you're interested in that's related to both of them and could be causing this to happen. So when you have two different factors that are associated with each other, this is called confounding, and it can cause you to look like you have an effect that may or may not be there. So my example for this isn't my favorite, but I'm hoping you look down below at the two combinations, and I'm hoping you notice that one of them is better than the other. You could look at low rate with no fee or high rate with a $50 fee. Clearly, one of these is more preferable than other, and there's really no way to separate this factor from each other. So this is definitely an example of confounding. So again, just to remind you, as I state down here below, a lurker is actually something that drives the other two. So it's already related to the two variables and makes it seem like they're actually related to each other, but when it's actually that they're related to this other single variable. And then confounding occurs when your levels for more than one factor are too related to the other factor's levels. So if you have the option of, you know, looking at two different treatments and clearly one of those treatments is probably a good combination and the other one is bad, it makes it very easy to say, oh yeah, well, I've confounded my experiment by offering these instead of offering something more balanced in nature. Alrighty. So a quick little example of this. A wine distributor presents the wine in two different glasses to a group of connoisseurs. Each person was presented with an envelope with the two different prices for the wine and corresponding to the glasses, and were asked to rate the taste of the two different wines. Is this experiment single blind or double blind or not blinded at all? So, so the person who's receiving this is not only receiving the two different wines, but they're also receiving two different envelopes that list the prices for these wines. So we are looking at multiple factors here. And this experiment is double blind since the individual who's handing these out really doesn't know which one's the more expensive wine than the other two. So you have no idea. If you'd like to see more interesting facts on this, there's I think it's a documentary about wine tasting in France, and they took a cheap $8 bottle and put it in a fancy label to see if people would rate it higher based on the fact that, you know, well, it looked nicer. And they did, which is kind of funny to me. It looks good, so it must taste good. Nope. Anyway, so the way we're going to analyze this is what is called the Anova, or analysis of variance. Anova. Oh, I underlined too much here. So that you've heard me say the word Anova before, that's what this is. We're analyzing whether or not the variation is large enough to be noticeably different. So is this variance that I'm seeing caused by the fact that this treatment group is different, or is it the fact that, you know, it's just caused by random chance? So, like I said at the very beginning of this process, hey, we are comparing means. So when you look at all of your combinations of factors to create your treatment groups, what we're going to be comparing is, are all of the means on average the same? When you look at the alternative hypothesis, I'm hoping you notice that it's the correct alternative. At least one of these must be different. So this is very much like Chi, where it was, hey, these are all the same, versus, oh, at least one of these must be different. So what we're looking at with our null is, again, we think of nulls as standard operating procedure, nothing's changed, aka there is no difference between my treatments. And then the alternative is at least one treatment result is different. For the first time in our history, we're also going to be performing what are called post hoc tests. This is, post hoc stands for after the fact, or it's Latin, not stands for, sorry. And the idea behind a post hoc test is, once we know at least one of them is different, we're going to be asking ourselves, oh gosh, we need to figure out which one of these is different, and can I tell? And that's exactly what we're going to be doing. Alrighty, so what criterion might we need to be able to test this hypothesis? Well, there's two things going on that could be causing the differences that we're seeing. So look at the two graphs below. The one on the left, I'm hoping you notice that they're all similar in one way and different than the other. Their means, or medians rather here, are all fairly close to each other, so they're not hugely different from each other. But when you look at how much they vary, or their spreads, those are completely different from each other. So although they may be similar on average, when I continue to look at all the possible values of the data, they are very different. Additionally, when you look at the one on the right, what you're seeing is, oh, well, these all have very different means. So very different centers. I'm trying to mark these out for you. However, their spreads are very similar. So the variation when I compare the groups is very much similar, but on average, they are very different from each other. And this is what the Anova is going to seek to balance out for you as we compare these groups. So we're going to use what's called the F statistic to do this. The F statistic is trying to balance the variation among groups in comparison to the variation between each group. And so what I just described is the numerator versus the denominator. So when I think about groups, think treatments. So I want to look at, is there a lot of variation in my groups, among them? And is there a variation when I compare them to each other? So when you think about this, what I'm really asking is, one of them super, super different from everybody else, or are they all different on average? We're balancing out the variation here together. So, and it should make sense that for a large F statistic, this would mean that there's just a lot of variation when I compare them in either measurement. So there we go. Another thing worth noting about the F distribution is that it has 2 degrees of freedom, one coming off your number of treatments and another coming off from your number of treatments in comparison to your total number of measurements. Let's look at the description of each of the numerators and denominators in more specifics. This should look fairly similar to some of the stuff you saw me doing in chapter 18, only now instead of measuring it across several variables, we're doing it across several factors or treatments. Okay, so the first thing we're going to look at is the variation caused by the treatment. So this is also called the in-between group measure, which I wrote here. So this is more or less comparing them across and compared to each other. So really we're looking at the difference when I treat them all as being similar. So this is why having similar means is kind of important, because then the grand mean here, the mean of means, is similar in value to everybody's mean, and therefore this distance will be small, and this distance right here would be small, and then my sum of squares between treatments would be tiny, and therefore this fraction would be tiny, is the idea. And that's if they are all similar. Get the idea? The next we look at the square error due to group variation. This is, oh, are they real different from each other? Not just in mean, but in spread. So we look at standard deviations, or variances, which, if you remember the relationship between standard deviation and variance, this is S squared. It's literally the standard deviation squared. Yeah, that's all the variance is. So remember, we calculated the standard deviation from the variance, and now we're just taking a step backwards and using the variance instead to say how spread are these. Whew. So the sum square error for the variances here is also weighted by the size of that sample or the observations in that group. So if you have groups of different sizes, this accounts for that. So if you are not very spread, but there were a lot of you, and there was another group that is very spread, but there was not a lot of them in that group, it would balance it out between this. So this is another reason why the ANOVA is called a balanced design. It takes size into account for its factors. And then we just average that across within the number of groups. So it takes into account the number of treatments that you have present, along with the size of your groups. So here's a table of how all of this is calculated. Put hearts and stars and all kinds of little marks all over this one because you're going to be using it a lot. This is how we calculate all of this. So usually we start by setting up the degrees of freedom grouping. So figure out your number of treatments that you have from all your factors and subtracting them, figure out how many people you observed, remove your number of treatments, and then the total will just be the combination of these two. So if you added these two together, you would get the bottom total value. And then we have sum squares for treatment and error. We would calculate the mean squares. Mean squares are calculated by taking just this value right here, the sum of squares, and then dividing it by the degrees of freedom for all of these. And that's actually true for this one as well. So I take my error and divide by n minus k. Oh, that looks kind of terrible. Hold on, let me write that better. I don't know why I said that. So we always think of this as being its sum square error divided by its degrees of freedom. So this will be the sum squares treatment divided by k minus 1. Oh boy, that's not any better. And this will be the sum square error divided by n minus k. And then you just take their ratio to find f. And then we used f like we have before when we've used f. F is a right-tailed test since it's summing everything. And so when we look at f, we want to think of it as a right-tailed test. We take the f value on that one's in particular f distribution, and we find the area to the right of it. You can really tell that I no longer have a working pen and I'm trying to do this by hand. It's super fun. Anyway, and that will create your p-value, your likelihood of getting that, or something worse or something larger. So one thing to keep in mind at f, it starts at 1. So the further you are from 1, the smaller your probability should be. If you have something really large in f and you get a really small p, it might be because your degrees of freedom are not that large, or you have something so small that it looks larger than it should be or smaller than it should be. Let's do an example. Oh, no, wait, hold on. No, yeah, I am going to do an example next. I'm going to talk to you about drums. Get excited. So toms. I know, it's the worst thing I've ever done in a long time. Is trying to boost their catalog sales by offering one of the 4 incentives with each purchase, either free drumsticks, a free practice pad, $50 off any purchase, or no incentive. So this would be obviously my control group because they don't get anything. So you're comparing your base sales to offering these 3 options to see if that will increase your sales. So here's what they did. You take the individuals from each of those treatment groups and you measure from these 4,000 offers, about 1,000 per treatment, and see what their spending looked like for a month. And here are so if we look at the box plot to the right, you'll notice that their means are all fairly similar in value. It looks like it's increasing across these groups, but these are just ordered it randomly. The spreads look good. They look pretty consistent. If you're having a hard time reading it off the graph, you can look at the summary in the table to the left. So their standard deviations are all pretty close. Their means are all pretty close, except for maybe the no coupon group. That one looks a little bit different. But that's what the ANOVA is going to tell us. Is this difference caused by random chance? Or is it because there actually is a difference between these groups? Yay, ANOVA. Also, Anova would be a really cool name for your dog. So when you calculate the Anova table, here's what you would get. Minitab will produce this for you, so don't think that you need to worry about calculating these all by hand, because some of those formulas are freaking terrifying. Anyway, So as you can see, the p-value is super, super small, so we will be rejecting the null hypothesis and conclude that, hey, one of these treatments must be different on average, aka mean, than the rest of them. Yay! So incentives, yes, appear to offer some alteration in spending pattern, although we're not really sure which of these groups is having the most effect. You might not be able to ever figure out which one of your treatments is doing the best job unless you change how to do your experiment, which would be a second stage experiment. All right. So what do you need to be able to do an Anova? Well, you need independence. This isn't too surprising if you're going to have randomization be present and required in your conditions and calculations, so that's not too shocking. Next up, we need the equal variance assumption. This is why I keep looking at box plots and trying to decide if they have about the same variation. And this condition is really required because we don't want to be the variation in treatment that we're seeing. We want to measure the variation we're seeing based on the different treatments, not because they all have different variances themselves. And this makes intuitive sense. If I'm trying to analyze whether or not they have different variants, if that's already similar, it's only the mean that can have an effect, the difference of the groups. So we really want similar variance to be a condition. And usually we just do this by looking at side-by-side box plots. All right. The next thing we need is the nearly normal condition. So one of the things to be careful about this is we want to do this in corresponding manners. Usually you can do box plots, or you could do a normal plot, or you could do histograms. Any of these is useful when it comes to calculating the nearly, checking, not calculating the nearly normal condition. And this isn't too surprising. F is basically a sum of student t distributions. So since it's a sum, if one of them is not normal when I add them together, it will not look normal, and that could be a bit of a problem. Let me show you what this looks like. So for the TomTomToms example, here's what the entire population looked like for the distribution. And I don't know about you, but I see 2 peaks. Normal distributions have 1 peak. And if you look at the QQ or normal plot, like we looked at in, I don't remember what chapter we did this in. So I'm going to draw my straight line in here as straight as I can. Okay, you can clearly see that this has some non-normality to it as it snakes through this. Darn. So it's got some problems. So there's 2 ways you would recognize that. Additionally, you should check all of your groupings to see if they're nearly normal. And they all exhibit bimodality, by modality in every single treatment. So this appears to not be successfully normal as we would like to be able to use the Anova. And this was also slightly something you could have suspected when we first looked at the the box plots of the data, because I had a lot of outliers, especially in the upper quadrant. So it appears that I had some heavy right tails there, some values that seem to be way high and above what they should be. So one of the things to keep in mind here is that since I failed one of these, it doesn't mean that you can't really say anything about this, but the sample sizes were pretty large, so I have quite a few outliers that are influencing the means. It could be quite possible that there is a difference about the means, since we can use the central limit theorem to say that this should on average have the same behavior. But so we're probably pretty safe in rejecting the null hypothesis here, even though it does not look normal. Alrighty. Let's look at another example. So a tutoring organization says that 20 students it worked with gained an average of 25 points on an IQ test when they retook the test after the course. Explain why this does not necessarily prove that the special course causes the scores to go up. Design an experiment to test their claim. So, since the students weren't randomly assigned, they elected to take this class. This is not a randomized design. In general, people who signed up for a special course were looking to improve their scores anyway, so they were working harder on average than an individual who's just taking the test for fun. We should expect them to perform higher. If you wanted to actually test to see if this was actually working, here's how you would do that. You would design an experiment. So you'd give the NIQ test to some volunteers and randomly then assign them to take this review course or not take it. And then after a bit, give them the test to see if the review course made a difference. Now, you might suspect that a student with a particularly low grade would benefit more from the course, but you know, how would you change your account to account for this suspicion? So after the initial test, you could, group the volunteers based on their scores. This is not random assignment, but rather a blocking. So if someone scored low, you'd randomly assign them or not, and then compare based on the lower grades versus higher grades to see if that made a difference. So this is a randomized block design instead. So you block for lower scoring individuals versus higher scoring individuals, and then randomly assign the treatment of taking the course or not, and see if that made a difference for the lower score as well. Okay. So the next thing we want to look at is what's called multiple comparison methods. So this is an optional topic within chapter 20. You don't really need this as much, and we're not going to be using it as we go forward all that much, but just so you've seen it, here's what is known as Bonferreri's method. If we know the difference between the means, and we actually know that they are different, we can try to measure by how much, and this is called the method of multiple comparisons. So the idea is that, why don't we just simply use a t-test to see if the differences that we test here, just the differences amongst each other. And this is sort of logical, but if you have multiple treatments that are maybe like 16 deep, this is a little bit gross. And the problem is that for every test you do, you introduce a probability of a type 1 error. And then, so since you're doing 16 tests, you have 16 times the probability of getting a type 1 error than you would if you just did one test. That's a little bit awful, error-wise. So one thing to keep in mind as you do this is you're inflating the value of t-star, aka the test statistic, as it accumulates across making all of these tests. So what happens is, as you make this type 1 error, it's increasing. So if you're going to do, like I said, like 16 comparisons, then your level of confidence that you should use should be adjusted for that error. So in order to reduce this so that you don't accidentally get more error than what you want, you can use this method to determine what level of alpha you should be using in order to make this work. Again, this is a method that you should use only if you want to do multiple comparisons instead of doing an Anova. You do not have to do this. So, and the other thing to watch out for is you can't have your your confidence interval shouldn't contain 0, because that would be a sign that there is no difference. Alrighty. So another thing to watch out for is people trying the Anova on observational data. So the Anova works really great for experiments because you're comparing multiple treatment groups, but since observational groups usually are assigning themselves treatment, you might not get as representative a sample. Usually you don't get equal spread. Usually you have a harder time getting near normality, and you might have one group so small that you can't actually use the central limit theorem to determine normality. So that's a bit of a problem. So I mentioned the fact that these are frequently unbalanced. Unbalanced means you have different sizes of all of your treatment groups, so you don't have groups that are the same size. You usually don't have any randomization, so you immediately fail the independence requirement. And you have no control over linking variables or confounding variables that might be messing with your results. So you can apply ANOVAs to observational data. It just might not be as useful as you might think. So be careful. You have been warned. Alrighty. Now for what I've been trying to get to. The MANOVA, or multifactor analysis of designed experiments, or multifactor analysis of variance. Whew, it's a little bit of a mouthful. See why I abbreviate this? It's like, whoa. This is when you have multiple factors that you want to measure their influence on behavior, and you want to see if maybe one treatment is superior to the rest, or if it's just one factor that is superior to the rest. So as a look at this, we have two factors that we're looking at, envelope design and frequent flyer miles. So you might ask yourself, is one of these going to cause this? So is it just a whole factor, like the logo, that's what does it? Or is it some combination of them together that does it? Like maybe having the logo and using double miles will cause the best response rate for individuals. I actually have this data, and we're going to go over it in your case study this week, so feel free to enjoy the future of this. So for the direct mailing example, the design was we took 30,000 individuals that were members, and we mailed them the 6 treatment groups, so combinations between standard or envelope or a logo, and 3 levels of mile rewards, either regular, double, or double use anywhere. And we did this to 5,000 individuals each, so they're all the same size. This will keep this nice and balanced. Alrighty. So after 3 months, we compare the results of their spending habits. So on the left, I have the total charges that they made in comparison to the standard versus logo group. Notice their spreads look about the same. Their means are a little bit off from each other, but not far enough to where I'm concerned. I am concerned that when you look at the mileage offers, it appears that although their means are almost completely exactly the same, their variations appear to be quite different. So there might be a difference that we see here when it comes to treatment groups. Alrighty. So in order to calculate the two-way ANOVA, you need to do sums of squares for not only everything, aka the total, but you have to do it for factor A, factor B, and the interaction of the two of them. We're going to rely on technology to do this. And the sum square due to error. So the table for this gets a little bit more complicated because your degrees of freedom are coming from two different factors. The first one, the second one, and maybe even a third one if you have another one, and how they interact with each other. So again, we're looking for, is it just one of them, is it the other, or is it how they interact with each other? Yep. So this looks gross, but it's okay because you notice that you have 3 p-values that you're going to have pop up from this. Oh my gosh. This really means that you have 3 hypotheses, one for factor A, one for factor B, and one for how A and B interact with each other, to asking if they have an effect on each other. And really when you think about the effect factor, it's, if one of them is constant, does this cause a change in the other? Let's look at how this looks for the direct mailing example. Alrighty, so here's the ANOVA table for it. So I had 2 options for envelopes, so 2 minus 1, 1. I had 3 options for miles, so 3 minus 1, 2. And when you multiply those together, you get 2. Yay! The sum squares coming off the data. And then the mean sum squares is taking the sum squares and dividing by the degrees of freedom. So you notice across that first row, it stays the same. And then the F ratio is calculated by looking at these individual factors as compared to the total error. So I'm hoping you notice that that first one is enormous. The second one, also enormous. But when you get to the interaction term, this guy, 0.5, hey, that's super small. I don't think that's going to work. Oh my gosh, and look at the p-value for that F. Oh no. So the interaction is not significant, but they're highly significant when compared to each other. Here's another way for you to look at this. So this is called an interaction plot. So we have standard and logo next to each other, well, sorry, not next to each other, in different colors, and then compared across the other factor, the mileage offer. And you notice that these are relatively parallel to each other, and this shows that there's really not much interaction happening between here. Now, if you had something that looked more like a V in either direction, that would indicate that, one of these is causing either an increase or decrease, where the rest of them is maintaining some sort of behavior. Another thing to look out for is if you have one line going kind of straight. Hold on, I'm trying to make this. That's not great. Oh, right. We'll pretend that's one nice straight line. And you have another that starts out parallel and then crosses. This is another indication that evidently the interaction between whatever these variables are is causing a big effect. It's causing a change. Watch for crosses. Watch for V's. So what can go wrong? Well, a lot. The ANOVA is huge with many places of things that you need to check. Watch out for confounding, look out for randomization. There are lots of bad things that can happen, good experiments. Oh, I have that written down. That's awesome. Bad things happen to good people. Oh no. Don't spend your entire budget on the first run. It's very rare for an ANOVA to not require a second run through your treatments, just so you're aware. Watch out for outliers. They can have a big effect on your data, and they will definitely inflate your errors, so be careful. And watch out for changes in variances. These are things that affect the ANOVA's output and can cause it to inflate. Alrighty. Be careful about drawing conclusions from observational studies because, again, you can't control treatments there or block out other factors that might be contributing to what you're seeing present. Be careful about generalization. I think that's true for everything in your life. Watch out for multiple comparisons. This is a much more complicated thing. Yes, it does require 3 hypotheses. And make sure you include an interaction term if you have more than one factor. When an interactor is significant, don't interpret the main effects themselves because it is the interaction that is causing the effect. So if on my previous example I would have gotten the interactor as being significant, I would have focused on it and ignored the significance of the other two because they were likely significant because the interaction was already significant. Alrighty. So what have we learned? Hey, the difference between an experiment and an observational study, what a randomized block design is, and what a randomized experiment is. Hey, the principles of experimental design, control, randomization, and replication. Replication is very important. This is becoming more of a hot topic nowadays than it used to be. So you want to create something that is replicable so that people can confirm your results. Remember, you don't necessarily have to have blocking, but it's nice if there's something that you think might have an effect on your experiment that you want to control. Just so you're aware, make sure you know what the words single, double, and control group are, as well as the placebo. You just learned some words. It's like glossary day. The main effect of what we've been focused on today is the Anova, the analysis of variance, which uses the F statistic, which is a sum of T statistics, to correctly, well, it's not really a sum, it's a combination of them, that allows you to test the hypotheses about the equality of mean across all of your treatment groups.